In this video, we will use exercise 3.23 to illustrate concepts related to sampling from a small population, which is section 3.3 of our textbook. Let's begin by looking at the concept of sampling with replacement. When sampling with replacement, you put back what you just drew. So for the example we're looking at, imagine that you have a bag with a distribution of colored chips, 5 red, 3 blue, and 2 orange chips. What's the probability that the first chip you draw is blue? Well, we can see that in this case, since there are 3 blue chips out of a total of 10 chips in the bag, the probability that we draw a blue chip is simply 3 out of 10, or 3/10. Now suppose that we did indeed pull a blue chip in the first drawing. If we're drawing with replacement, in other words, that means if I pull a blue chip, I put it back into the bag before my second drawing. What's the probability of drawing a blue chip in the second drawing? Well, again, for the first drawing, we had a distribution of 5 red, 3 blue, and 2 orange. That distribution does not change before we do the second drawing because we've now put the chip back in the bag before the second drawing. So the conditional probability that the second chip drawn out of the bag is blue, given that we drew a chip that was blue out of the bag the first time and put it back, is going to simply be 3 out of 10, or 3/10. Now continuing with sampling with replacement, suppose that we actually pulled an orange chip out of the bag in the first drawing. If we're drawing with replacement, what's the probability of drawing a blue chip in the second drawing? Well, again, the first drawing, we see that there were 2 orange chips out of 10 for the first drawing, but we put that orange chip back in the bag, so before the second drawing occurs, we have the exact same distribution of colored chips in the bag that we had at the beginning. Therefore, the probability that the second chip drawn out of the bag is blue, given that the first chip drawn out of the bag was orange but then put back in the bag with replacement, would be exactly the same as what we had in the previous slide. It's 3 out of 10, or 3/10. So if drawing with now let's take a look at another example. If we're drawing with replacement, what's the probability of drawing 2 blue chips in a row? Well, we know that before the first drawing, the distribution of the chips is such that there are 3 blue chips out of 10 in the bag. If we're doing it with replacement before the second drawing, the distribution is exactly the same again. So using the general rule for multiplication, in other words, we want to find the probability of there being 2 blue chips drawn in a row, probability of blue and blue. Using the general multiplication rule, that would be the probability that the first chip is blue, which would be 3 out of 10, times the conditional probability that the second chip is blue, given that the first chip drawn was blue, and again, of course, replaced back into the bag. That would also be 3 out of 10, as we saw on the previous slide. So the probability overall of drawing 2 blue chips in a row would be the product of those two probabilities, which is 9/100 in this case. So let's summarize everything that we've seen in these examples of sampling with replacement. When drawing with replacement, the probability of the second chip drawn being blue does not depend on the color of the first chip that was drawn out of the bag, since whatever we draw in the first drawing gets put back in the bag. We can see that summarized with the conditional probability notation that's shown below, where it says that the probability that the second chip drawn is blue, given that the first chip drawn was blue, is exactly the same in this case as the probability that the second chip drawn is blue, given that the first chip drawn was orange, with the assumption again that in between the drawings, we are putting the first chip back in the bag. In addition, this probability is equal to the probability of drawing a blue chip in the first drawing, since the composition of the bag never changes when sampling with replacement. In other words, the conditional probability of the second chip being drawn, let me restate that. In other words, the conditional probability of the second chip drawn being blue, given that the first chip drawn was blue, is exactly the same as the probability of just drawing a blue chip out of the bag for the first drawing. When drawing with replacement, the draws are independent. Let's now use our example to talk about sampling without replacement. When drawing without replacement, you do not put back what you just drew. So suppose that, using the same distribution of chips in a bag that we've been talking about, suppose I pulled a blue chip in the first drawing. If drawing without replacement, what's the probability of drawing a blue chip in the second drawing? So again, for the first drawing, we had 10 total chips, 3 of them blue. But now before the second drawing, I'm 1 blue chip less than I had before, and there are only 9 chips total in the bag. So the probability of drawing a second blue chip out of the bag, given that I drew a blue chip the first time without replacement, is only 2 out of 9, or approximately 2,222 10,000ths. Notice that this value is less than the 3/10ths, or we could also say 3,000 10,000ths that we had previously when we were sampling with replacement. So now suppose that if we're drawing without replacement, what is the probability of drawing 2 blue chips in a row? Well, again, the first drawing we have 3 blue chips out of a total of 10. The second drawing we have only 2 blue chips out of a total of 9 if we drew a blue chip on the first drawing. So using the general multiplication rule for finding the probability of getting 2 blue chips in a row, we first take the probability that the first chip drawn is blue, which would be 3 out of 10, and then we multiply that by the conditional probability that the second chip is blue, given the first chip was blue, which is 2 out of 9. We multiply those two values together. We get 1 out of 15, or approximately 667 10,000ths. Again, notice that this value is less than what we found for the same probability that we calculated when sampling with replacement. In that case, we saw the value was 900ths, or we could also say that is 910,000ths, which is larger than the value we have just calculated. So let's summarize what we have just seen about sampling without replacement. When drawing without replacement, the probability of the second chip being blue, given the first was blue, is not equal to the probability of drawing a blue chip in the first drawing, since the composition of the bag changes with the outcome of the first drawing. And again, I've shown that represented in probability notation, that the conditional probability of the second chip being drawn being blue, given that the first chip drawn was blue, with no replacement in between, is not equal to the probability of drawing the blue chip on the first drawing. So, summarizing this, we can say that when drawing without replacement, the draws are not independent. And it's important to notice that in this case, the general multiplication rule is important to keep in mind when we don't have independent draws. This is especially important to take note of when the sample sizes are large enough or the population is small enough that we sample more than 10% of a population without replacement. If we were dealing with, say, 10,000 chips in a giant bag, taking out one chip of any color would not have as big an impact on the probabilities in the second draw. And essentially in that case, we could assume that the drawings are independent and we would not need to use the general multiplication rule in that case. But when we are dealing with a case like we just looked at, where the sample in this case is more than 10% of the total number of chips that we were looking at, then we would need to take into account the general multiplication rule.